we will see the benefits and limitations of the decision support tools. You can see that the benefits are much more than the limitations. The most important benefit is that they extend decision makers' ability to process information and knowledge, and they also extend his or her ability to tackle any complex problems. Of course, they shorten the time that is associated with making a decision. They can also improve the reliability of a decision-making process or the reliability of an outcome. They also encourage exploration or discovery. The decision maker can experiment through the decision support tool. They can generate new evidence to support decisions, and they also can improve users' ability to correctly identify any important information in the environment and translate that information into viable options. The limitations that surround the decision support tools is basically that the power of a decision support tool highly depends on the computer system that the tool is built upon. It also depends on its design and the knowledge that the system possesses. Considering that the database knowledge system is one of the most important systems of component of the decision support tool. Moreover, the natural language processing is not yet supported due to language and command interface limitations. And finally, the support tools are normally designed for a specific application, and they do not perform well outside the scope of this original application. We have a specific decision tool for a specific area of problems. Okay, now we're on the spreadsheet database decision support tool, and I will also present to you a spreadsheet-based decision support tool that we have created for evaluating the alternative QLs. A decision-based decision support system or tool is a decision support system that integrates in a spreadsheet environment the inheritance of a programming language and a user interface developer. The spreadsheet supports all the components of a decision support tool. It has a knowledge system, and through the knowledge system, the spreadsheets can easily store large amounts of data in rows and columns, and on multiple worksheets. The problem processing system of a spreadsheet, it is basically the fact that the spreadsheet software can perform many calculations through the formulas and the functions that it contains, or it can use a programming language such as the VBA that the Microsoft Excel has to solve the model. And of course, the GUI system, in which most spreadsheets offer a variety of GUI options, from the very basic formatting to drawing tools to more advanced GUI features such as user forms or controls. If we decide that we want to build a spreadsheet-based decision support tool, they are basically 6 steps that we could follow through this procedure. The first one is we have to overview the application and model development. During this step, we can create a layout of the entire application. We can designate the flow from the user input to the model calculations to the output and outline everything in more detail. During the next step, the worksheet step, we can determine how many worksheets the programmer requires to best handle the inputs, the calculations, and the output of the decision support tools. Basically, we want to see how many worksheets are required to build a reliable and functioning spreadsheet-based decision support tool. Then we have the user interface. Here we outline what interface the programmer requires to receive input from the user and navigate him or her user through the application. Then we have the procedures. Here we outline what procedures are required to receive the input from the user, to perform the calculation through the model, and display the output through the presentation system. We also need to have some resolve options. Here we just have to decide what resolve options the user will be given. For example, we can allow him to change some parameters when run the beginning. And finally, we have the testing and final packaging. Here we just have to ensure that the application is properly functioning and it has a clear and professional appearance. We have developed a decision support tool for the alternative seed fuels. Basically, this application allows the users to calculate their seed operational costs and compare this cost with the operational costs of alternative fuels. Here also in this spreadsheet, the user can also compare the investments of the alternatives. The outline of the spreadsheet is basically that the user begins by creating the profile of his or her seed through entering certain parameters. Once the users have created the profile of their seed, and time to the input worksheets to edit it. This is the resolve option we provide through the decision. And the basic aim of the decision support tools is to solve the investment. I can hear my voice. Can you hear me?
Yeah, it was a problem, I think. Okay, you can continue.
Well, the decision support tool solves the model and displays to the user various results regarding the cost, the operational cost, and the investment of the alternative seed fuels. And the model, the basic ability of the model is the comparison of the alternative fuels. By comparing the alternative fuels, promotes the most cost-efficient solution based on certain financial parameters. The user inputs are parameters that focus on the profile of the ship, on the investment, and other operational costs, such as the maintenance costs. The users also input the fuel prices, but we will see that as we will examine the ship. The model outputs are the fuel investment costs and operational costs, and also the ranking of the fuels based on those parameters, on those outputs. And finally, we have 6 worksheets in this particular application. We have the welcome sheet, we have 1 input sheet, we have 1 output sheet, which is very important too, and we have 3 model sheets where all the calculations are happening. And this is the welcome sheet of the decision support tool. Here we just have a description of the tool, and it says to the user of the tool what this spreadsheet is all about. And the user just presses on the start button to begin the decision support tool running. By pressing to the start button, directed to the input spreadsheet. This is the input and here the user has to enter all the parameters related to his or her ship. Those parameters are divided in 6 basic groups. The first group of parameters are the general particulars of the ship. Here the user has to create a general profile of the ship. He has to enter ship's name, the year it was built, the type of the ship, the dimensions of the ship, the age of the ship, the estimated operational life of the ship. Just to have a general profile to let the user know that he is currently making all the calculations for a particular this particular ship. The second group of parameters is the operational profile, and here the user enters parameters related to the total number of days that the ship operates within a year, the percentage that the ship spends within a self-emission control area. Also, here the user has to input data related to hours per day that the engines operate. We divide these parameters into 2 major subgroups. We have the main engines and the auxiliary engines. And for each type of engine, the user has to input the operating hours per state. We have 4 basic states. We have the number of hours the ship operates at sea, the number of hours that the ship operates while it's loading and unloading, the number of hours that the ship operates while mooring, and the number of hours that the ship, the end of the ship, are idle. The user has to input those data, both the main and the auxiliary engines of the ship. The third group of parameters refers to the engines of the ship. Again, this group of parameters is divided into the main engines and the auxiliary engines of the ship. Here again, we basically build a general profile of the engines. We have a type of the engines that the ship uses, the number of the engines that the ship uses, and the power of its engine. Sorry. Other parameters that this group contains is the number of main engines that operate per stage. The user has to input the number of the engines, of main engines that the ship operates while is at sea, while it is loading, unloading, maneuvering, and being idle. The load of the engine, again, based on the state of the ship, at sea, loading, unloading, maneuvering, and being idle. And another that the user has to input here is the average specific fuel consumption of the main engine. Here, this group is divided into parameters based on the specific fuel that the ship burns. In this example, in this decision support tool, we only consider 4 basic options, including the HFO option, which is currently what the user is operating with. So we have the HFO option, we have the MGO option, we have the option of using HFO with scrubber, we have the LNG option and the LS-HFO option. This is the profile that the user has to create for the main engines. We follow the same pattern. Auxiliary engines, the user has to input the type of auxiliary engines the operates with, the power of these engines, the number of engines, and again, the number of engines that operate per day. What it is at sea, loading, unloading, maneuvering, and saying the average engine load and the average specific fuel consumption. The fourth group of parameters contains all the investment cost parameters. Again, here we divide the engines into the main engines and the auxiliary engines. In the main, and the user here has to choose whether he performs full or a partial retrofit, and he also has to input the cost of this retrofit, the number of engines that are partially retrofitted. If the user decides to retrofit just 2 engines, then he has to put that information in the issue support. The day that the ship spends on the and also have to input costs of the profit loss due to the fact that the ship stays outside operation due to freeze, and the cost that is needed for the training of the crew in this fuel. Again, we have to say for the auxiliary engines, and we're deciding to share with you the Excel part. So this is the welcome screen, worksheet. We press on the start button. Can you see the Excel file? Do you see it?
It is only cannot see
No. Wait.
That's perfect. We can see the Excel file.
Okay. So here we have the first group of parameters, the general particulars. We put in ship name, year B, the ship type, the tonnage, the average speed, the age of the group, and several deadweight, and several other parameters that are related to the general profile of the ship. We now have to build the operational profile of the ship. We have to input the number of days that the ship operates, the number of hours that the main engines of the ship operate per stage, the percentage of time that the ship operates in within a self-emission control area. As I previously described, we have to create the engines profile of the ship, both for the main and engines. On the fourth table, input all the parameters related to the investment cost. The investment cost is divided per alternative solution. We input here the retrofit cost for the MGO solution, for the HFO scrubber solution, for the LS-HFO solution and LNG solution. Well, we do the same thing both for the main and the auxiliary engine. The fifth table is the operating expenses, or what else they call it, OPEX. Here we input the bunker price, dollars per ton, for the MGO, the HFO, the LS-HFO, and LNG. We have obtained these prices from this site, is the shipandbinder.com, and these prices are for ports. We also have to input the maintenance cost of the fuel and the job system. Again, for each alternative solution, we just type our maintenance cost here. I can change it now to see. These are all cells that the user can edit. He just has to input his data here. And here we just have to put the daily profit loss due to space reduction caused by retrofit. And this usually applies only on the LNG solution, because they have some large tanks they have to put on the ship, and something that minimizes the space that the ship could use to accommodate passengers, or if it was a car carrier, to accommodate cars. And finally, we have the financing options, all the parameters that are related to financing the investment. Here we input the financing scheme. We can finance our investment through our equity capital. I could just put 100 here, 0 here on the grant, and 0 on the foreign capital. The foreign capital is basically a loan, or we could put 50% of equity capital. We could also get a grant, let's say around 35%, and this remains a 15% for a loan we have to take in order to finance our investment. If we take a loan, we have to input here the loan period in years. Here we say that the maximum loan period has to be 15 years, because this is basically the horizon that we investigate. We investigate the investment on the alternatives for 15 years. We put inside here the annual interest rate of the loan, the cost of equity, and the cost of grant. After once the user has input all these parameters, he can then click on the View Results button. Basically, the report. If the user has changed his mind, he can then go back to the parameters and change some of that. This is basically the resolve option that the DST file offers. Here we have assumed that the ship only operates within a SECA area, or emission control area. And by operating 100% in self-emission control area, we have calculated that the current annual operational cost of a ship currently using the HFO is around $6 million. Here we have the utilization factor. Not operate 365 days a year and 24 hours a day. It only operates 250 days a year and for specific hours per day. So the utilization factor is 63%. We have also calculated the power utilization factor, which is basically the percentage that the ship uses its power, the power that contains from the main engines. And we have also calculated the operational cost per stage. We clearly see that at sea, the at sea state has the highest operational cost, and the next highest operational cost is while the ship is maneuvering, then we have loading and unloading, and while being idle is the lowest. Here we can change the percentage of SECA operation and see how certain parameters, result parameters change. I can press this scroll bar. By pressing this scroll bar and changing the SECA operation percentage, you can see that the parameters below on the comparing alternatives to existing situation are changing as well. Do you see it? Yes. Okay, we can go back to the presentation and then return to the Excel file. Let me just present to you the assumptions of this decision support model. As I previously said, for practical and economical reasons, we only consider 4 alternate solutions. We can either use marine gas oil as an alternative fuel, or use LSHFO as an alternative fuel, or move on to a more to different solution and use either LNG or HFO with scrubber. These are basically the emissions we can see that the IFO, which basically the heavy fuel oil that the ship currently operates with, has a self content of 3.5, which is really high, and the LSHFO has a self content of 1% or 1.5%, which is the limit that the EU legislation requires. The MGO has even lower percent, is only 0.1, while the LNG has 0% of sulfur content. These three solutions are all within the limits that the EU legislation requires sulfur dioxide emissions. Let's describe now what these solutions are. The MgO and LS8FO are basically considered the reference case. It's the most easiest solution to implement. We can switch to a low sulfur fuel without making any big drastic modification and the seed of oil. The investment cost for switching to MgO and LNG is minor compared to the other two solutions. However, extra attention should be paid in the maintenance of the engine, something that may result to an increased maintenance cost compared to the HFO, the initial stage. The HFO with scrubber solution, basically the scrubber is a filter that uses water to wash out the sulfur from the exhaust. With the scrubber solution, the ships can still operate within the sulfur emission control areas using the HFO, the heavy fuel oil, considering that the scrubber minimizes the sulfur dioxide emission to less than 0.1%. The scrubber is a solution that is installed on both the main and the auxiliary engine. And in order to install the scrubber, we have to perform some kind of retrofit. This results in substantial investment cost, comparing to the MgO and the LS8FO solutions. Our fourth option is to turn our ship into using LNG as an alternative fuel. LNG has the ability to reduce the nitrogen dioxide emissions up to 85%, while it completely removes sulfur dioxide emissions and particulate matter. And the use of LNG as a fuel requires a retrofit of the main engine of the ship, and the fuel system has to be present on board. This solution can still run on a low sulfur fuel, which can be either MgO or LS8FO. And the problem with the LNG solution is basically the fact that the investment cost, it is much higher than the scrubber solution. And also, we have to put the LNG tanks on board, something that basically minimizes the space that the ship uses. Other assumptions that the model is based on is that the calculation of the main engine and auxiliary engine fuel consumption is based on the average fuel consumption of a specific type of engine. Also, the retrofit of the engine for alternative solutions can be either partial or full, as I previously said, and the cost that the user has to input as the parameter to the respective tables refers to the cost of each type of retrofit. So if the user chooses to do a partial retrofit, then on the investment cost, he has to input the cost of the partial retrofit. If he chooses to do full retrofit, then on the respective cell, he has to input the cost, the total cost of full retrofit. Again, we have to do the same if we decide to retrofit the auxiliary engines as well. Another assumption is that the number per state, the number of engines that the ship uses while operating is the number of engines that we will retrofit if we decide to move on to an alternative solution. So if we are at sea and we operate with 2 engines, when we analyze the alternatives, can you please repeat the question?
Yes, this is Andrea. So my question is why there is always a negative difference in operational expenses, even for LNG, which cost less than heavy fuel oil.
You're talking about this is not right. Well, this difference is between the operational cost of LNG compared to the operational cost of the ship operating with HFO. HFO has much smaller price, a lower price, from LNG. This is basically why we have this difference, the negative numbers. Am I clear?
Okay, thank you. Because when LNG costed much less than heavy fuel oil.
The price of LNG is less than the price of MGO and the price of LSHFO, but it is higher than the price of HFO. And that is why we have this negative difference. So, convenience. What do you mean? Yeah. Okay. You know. Ah, interesting. What were now I have to change it. Okay. What were your results? More. What did you consider? And you came to that conclusion? Only just the fuel prices or what else? Such as too long to explain. Okay. By time. Okay. Okay. Let's move on. Okay. We also said we have 3 model sheets. This is one of the model sheets. Here we calculate, anyway, Matthias, okay. Here we just calculate the operational cost of
Eleni,
each
can you hear me?
Yes.
Give me a moment in order to give the microphone to Andrea in order to finalize what he just asked. And I will give you the microphone after the question of Andrea. Is it okay? So Andrea, you can finalize your question and your comments, and then Eleni will answer.
Yes, Andrea speaking. Can you hear me? Can you hear me? Okay. I cannot hear you, but anyway, I go forward. So basically, my thesis analyzed the technical and economical aspect, but was focused on the willingness of ship owners to consider other solutions like scrubbers, LNG, compared to the use of marine gas oil. Because 2 years ago, the price of marine gas oil was more than $1,000 per tons. Now I know that Brent price collapsed, so maybe the situation changed. At the end, the result of the thesis was that Italian ship owners decided just to wait for new rules and new things. So at the moment, not all, but most of them were not ready to start refitting projects, because the future was a little bit unknown.
And we're here now to evaluate those alternative solutions. We mostly focus on the price. Price because it is a parameter that fluctuates extremely. It is not easy to predict. And of course, it is interesting to evaluate.
Okay, thank you. If you want, by private mail, I can share my thesis with you.
Oh. Okay, so we have the cost sheet. Yeah. You can share your thesis with me. That would be interesting. Okay. So here we calculate the operational cost of each solution. Then we compare the operational cost of the alternatives to the existing state. The existing state is the ship burning the heavy fuel oil. This is why we get the negative difference that Andrea previously said. It's basically because all the other solutions are much more expensive than the current solution. And on the next step, we compare the operational cost of each solution to an alternative one. We basically have created 6 possible combinations. We compare LNG to MGO, HFO with scrubber to MGO, LS-HFO to MGO, LS-HFO to LNG, HFO scrubber with LHFO and HFO scrubber with LNG. 6 possible scenarios. This is basically the assumptions of how the cost is calculated. Until 2019, on the energy solution, when the ship is not operating within a sulfur emission control area, can still burn the HFO fuel. If he operates inside a sulfur emission control area, the MGO solution, which is, as we said, a fuel with lower sulfur content. After 2020, the same ship has to use the MGO on both areas, inside the sulfur emission control area and outside the sulfur emission. Again, we have created the same table for the HFO with scrubber solution, the LS-HFO solution, and the LNG solution. Again, the basic difference between all those 4 solutions that the HFO with scrubber can still burn the heavy fuel oil. The ship only to put money on investment for the scrubber and still run on the HFO, which is the fuel with the lowest price between the 4 of them. Assumption we have made in calculating the operational cost, fuel cost, is that we assume that when the ship is outside the control area, it burns the fuel with the lowest per BTU. Another model sheet is a cash flows sheet. Here we have created the cash flows for all 6 combinations. Cash flows were calculated for a period of 10 years, and here we put on the investment, the money needed for the investment, and we also calculate basically the benefit in OPEX between the different alternative solutions. Here we also put the installment of the loan if the ship owner decides to take a loan to finance investment. We calculate these cash flows both considered based on the total capital and based on the equity capital. Model sheet is the financial sheet. Here we use all the information deriving from the cash flow sheet for the alternative fuels, and we calculate certain financial parameters such as the net present value, the IRR, period, PI, profitability index, and we compare the six combinations based on those parameters. We calculate these parameters, financial parameters, based on the two different cash flow tables we have created, meaning we calculate them based on total investment and we calculate them based on promoter's equity, the equity capital. And through these calculations, we obtain the report sheet, which is the output sheet of decision support tool. The report sheet has several graphs and tables that describe what are the results based on the parameters, the input parameters that the user has entered on the parameter file. Here also the users have the ability to use the scroll bars to basically perform a multivariate analysis of several crucial parameters, such as the percentage of operation, the price of the fuel, and the age of the ship. As I previously showed to you, here we have the option, the button, to go back to the parameter sheet, change some and resolve the problem. Just please allow me to show you the Excel file. This is the report. I described to you the first half, the first third previously. Here we can change the percentage of self-permitted control area operation. It's currently 32%. I can increase it and see below the difference between the alternatives and the original state, the 84 state. We can see that as the percent of SECA operation increases, the difference of LNG and the HFO decreases, while all the others increase. You can see our report sheet. I have the difference between the HFO and the. Here we have, we can see the difference between the HFO state and the alternative solutions. And also, you just scroll through either increase or decrease the fuels. As I increase the price of energy, I will see that energy is extremely expensive. 12 meters. If I the price of, you can see that the LNG and the LS80 solutions are we have a positive difference here. We can do the same with the alpha. And here the result based on the difference on the based on the difference between the average of the alternative and the HFO gives us the most here the most efficient solution based on the is LNG. Fuel that is extremely difficult to predict. You can see the fluctuations here. This graph refers is for the port of Piraeus. We can see that in July the price of HFO was around 110. The price of LS80 was around 700. The price of NGO was around $950. And we can see the high fluctuations that the price show, as well as the seasonality that they show. In July, the price is much higher than January. In January, it takes its lowest price molecules. Okay. Due to the fact that the prices are so difficult to calculate, this puts an extreme risk into our process. This graph also shows the prices of HFO, MGO, and gas in euros this time. This historical analysis is for the period of 1991 until 2013. Yeah, we can see that the MGO is the most expensive fuel. Then HFO follows. The gas LNG is the least expensive fuel. Here we can see the increased fluctuations of the prices. What I show you with the scroll bars, we can increase or decrease through the scroll bars the prices or the percentage of saturation and obtain different results from the initial. And we move on to the next one. Sleep life is also an important part we have to consider when analyzing and evaluating the alternative. Basically, important here is the payback period of the investment. And here we have comparing HFO with scrubber to we have a payback period of 1 6.2 years. This means that if we have currently that is aged 10 years old, and we can see that within a year or two, the investment will pay back its money. On the contrary, when we evaluate HFO with scrubber against LSHFO, we see that the payback period is almost 14 years. So if we have a seed that with operational life of 25 years and it's currently on its 13th year, this returns us 27. It means that the investment will not pay back its money within the operational life of the. Here it shows us that when we evaluate HFO with scrubber against LNG, there is no payback period. This is probably due to the fact that no payback period for the period we estimate here the 15 years, for a period of 15 years. So within those 15 years, there will be no payback when we compare HFO with scrubber to LNG. This is probably due to the fact that LNG has much higher investment cost than scrubber, and that the price of HFO is lower than the price of LNG. Well, I previously told you that we calculate certain financial parameters. Well, what are those parameters? What those parameters are? I'm not sure what is your back. So I decided to make a slide explaining what financials are. So we have the net present value, which is the key factor. This basically tells you how this investment compares compares with your investment. If we have a positive net present value, this means the investment is better than the alternative. If we have a negative net present value, this means that the alternative investment is better than the one we're evaluating. Other factors that we calculate is the internal rate of return, or IRR, which is basically the interest rate at which net present value of cash flow, the cash flows we calculated through the cash flow spreadsheet. And these cash flows are both negative and positive. We include all of them in calculating the internal rate of return. So this internal rate of return gives us the interest rate. These cash flows are equal to 0. It is basically used for evaluating the attractiveness of an investment, the same way that the net present value is used. If the IRR of a new project exceeds a company's required rate of return, that project is desirable. If it falls below that required rate of return, that project would be rejected. Another parameter we calculate is payback period. This is a really important parameter because it is whether to undertake the project or not. As long the longer the payback period is, it typically says to us that the investment will not peak investment. The financial parameter we calculate is the profitability in PI, which is basically a measure that identifies the relationship between the costs and benefits of a proposed project. Something that is lower than 1 basically indicates that the project value is less than the initial investment figure. We have set a loan rate of 7%. Our investment horizon is analysis years. We have obtained a grant 5% of the grant. The HFO price is $350 per ton. The NGO price is $589 per ton, and so on. So for the section is 15%. So these are the results we obtained based on these parameters. According to those parameters, the most viable solution is HFO with scrubber. It has the highest net value. It is accepted by the IRR parameter. Its payback period is really low. It happens within a year, and it has a profitability index more than 1. Also, we see a big difference between the spread, the price of the HFO parameter should not be accepted. They have a negative net present value. They are rejected by the RR parameter. And their payback period is really big. And they have a negative profitability. Basically means that there is no benefit. If we see investment, if we analyze the investment of equity, slightly results. Here, the most desirable solution is LNG when it is compared to MGO. And now let's see how the payback period changes. When we consider different percentages of self-emission control operations. We have here different spread values. We evaluate LNG and MGO, and what we can conclude from this diagram is that when the percentage of time inside a self-emission control area increases, then the payback period when comparing LNG and MGO, we can see when we spend 25% of the time within the sector area, the payback period is much higher. Here we consider the average of when the price $7 per MMBTU, $9 per MMBTU, and $11 per MMBTU. So considering those three different scenarios of prices, the payback to HFO is 6.7 years. When the price is $7 per MMBTU. When the price of LNG increases to $9 and $11 per MMBTU, there is no payback to HFO with scrubber. When we compare LNG with LSHFO and the price is $7 per MMBTU, then the payback period in favor of 2.6 years. And if the price of LNG increases to $9 per MMBTU, then the payback period increased by around 8 years, while if the price increases even more to $10 per MMBTU, there is no payback compared to LSH. And on the final column, we evaluate the three different price scenarios against payback. So when the price of LNG is $1 per MMBTU, the payback LNG here 0.48. When the price is $9 per MMBTU. It will increase just a bit, 0.6 years. But when the price of LNG increases $10 per MMBTU, the payback period against NGO is 1.1. You see here that compare LNG to NGO, which price is much higher. The payback period is less. What we have concluded from this study that we reduce or completely and existing tankers to one of the alternative fuels. Those should not study either NGO or FO, LNG or AFO with scrubber. The NGO solution, due to its higher price, the highest operational cost comparing to the other solutions. So the investment cost of this may be the smallest one. And AFO with scrubber solution is much higher, much lower investment cost compared to. However, the long run it will produce operational cost due to the price of LNG when we consider dollars per MMBTU is much less than the price of HFO. The LS-HFO, it has a higher price on HFO, but it has a lower price on NO. It could be a good alternative compared to NGO, but it is less attractive than LNG, again, the operational cost. And also, as the self-reproducible layer percentage of time increases, then LNG becomes more attractive as solution compared to NGO. And comparing LNG with the other solutions, with scrubbers